Good afternoon, everyone. My name is Joe O'Rourke. I'm a graduate student at Caltech working with Dave Stevenson in planetary science, and I'm here today to discuss the problem of how to keep a magnetic field going on a little planet called Earth. So our study is aimed at resolving what Peter Olson has called the new core paradox. Now, paleomagnetic evidence reveals that Earth's dynamo has survived for at least the last 3.4 billion years. And vigorous convection within Earth's liquid outer core is needed to drive this dynamo, which would otherwise start to dissipate in about 10,000 years. The paradox arises because the thermal conductivity of the core has recently been revised upwards by a factor of 2 or 3, and this is based on both first principle calculations and diamond anvil cell experiments. This is a problem because high thermal conductivity implies that the inner core is less than 1 billion years old. It needs to grow very quickly in order to provide enough buoyancy to sustain compositional convection. The paradox is that thermal convection alone cannot sustain the dynamo before the nucleation of the inner core, unless you invoke extreme cooling rates or geochemically dubious levels of radiogenic heating. So our proposal is that the precipitation of magnesium-bearing minerals from the core can serve as an alternate power source. And for decades, we've known that the density of the core is about 10% less than that expected for a pure iron-nickel alloy. And identifying the light elements responsible for this deficit has remained a central problem in geophysics. But despite being the fourth most abundant element in Earth by mass, magnesium has usually been rejected as a core constituent. And this is because magnesium's solubility in iron is very low under ambient conditions. However, few experiments have probed the extreme high pressure and temperature conditions that are actually relevant to core formation. Recent diamond anvil cell experiments by Nomura and Hiroshi suggest that the solubility of magnesium in iron becomes significant at temperatures around 5,000 Kelvin. And recently published first principles calculations show that there might be a low solvus closure temperature in the Fe MgO system. So these new results have motivated us to consider whether the partitioning of a small amount of magnesium, roughly 1 weight percent, into the core is consistent with everything we know about how the core formed. So here is a popular picture for the formation of the core. Impacting planetesimals disaggregate in a magma ocean that overlies a mostly solid region. And the metal from these planetesimals equilibrates in a pond at the base of a magma ocean at the ambient pressure with temperatures near the prototype liquidus. Then the metal is transported quickly to the core in diapirs without much further equilibration. And as a consequence of these processes, the mantle becomes depleted in siderophile elements like nickel, cobalt, chromium, and vanadium. And their observed metal silicate partitioning behavior suggests a pressure of equilibration around 54 gigapascals, corresponding to a temperature near 3,500 Kelvin. One problem with this picture is that light material becomes more soluble in metal as pressure and temperature increase, meaning that as Earth grows, the core should have a higher light element concentration. And this can cause a stable stratification to develop at the top of the core, a very large one, that will inhibit dynamo activity. Another issue is that simulations of planetary accretion indicate that the last stage of Earth's growth likely consisted of scores of collisions between planetary embryos that ranged from Moon to Mars size. And after a giant impact, material can partially equilibrate at temperatures that are thousands of Kelvin above the prototype liquidus. For example, simulations of the moon-forming impact indicate that it heated parts of Earth up to maybe 10,000 Kelvin and possibly even caused complete melting. And also, these giant impacts may provide the vigorous mixing that is necessary to overturn the stable stratification in the core and restore its homogeneity so that the dynamo can proceed. So any realistic model of core formation needs to incorporate both giant impacts and equilibration at the base of a deep magma ocean. Metal silicate partitioning is usually modeled using redox reactions. Here I've written the equations for magnesium, but you can write similar ones for silicon, oxygen, and the siderophile elements. Here we have MgO in silicate and Fe in metal reaching an equilibrium with FeO in the silicate and Mg in the metal. We can write the exchange coefficient for this reaction, K sub d, which is just the product of the molar abundances of Mg and FeO divided by those for MgO and Fe. And this exchange coefficient is just the product of the partition coefficient, d sub m, and the oxygen fugacity relative to the iron Wüsteit buffer. And diamond anvil cell experiments allow us to write parameterizations for the exchange coefficient in terms of pressure and temperature and some constants. Now, for any element, the partition coefficient D is just the ratio of the molar abundances in the metal and the silicate, meaning in the core and the mantle. So we use these equations in a computational simulation of core formation. In order to do this, we use something called Markov chain Monte Carlo analysis, or MCMC. And this is a Bayesian statistical technique that is widely used in order to deal with models that have very high dimensionality. What we want to know is the probability that our model is true given the data, and this is called the posterior. Now, Bayes' theorem says that this posterior probability is proportional to the likelihood that the data are produced by our model times the prior probability that our model is true. And our model has many free parameters. So we model core formation in 2 steps. We assume that a fraction f of the core equilibrated in a magma ocean with some pressure and temperatures constrained to the prototype liquidus. Then the remainder, 1 minus f, equilibrated in the aftermath of a giant impact with temperatures simply constrained above 4,000 Kelvin. And we use a simplified Earth composition, and we model the partitioning of silicon and oxygen and the siderophile elements, the 4 that I mentioned earlier, using equations from the recent work of Sieber et al. And the formal experimental errors presented along with the nominal values of the exchange coefficients give us our prior probability distributions. And then we use equations from Nomura and Hirose to model the partitioning of magnesium. And the data that we compare our model to are the estimated values for the likely range of the actual partition coefficients for the siderophile elements on Earth. And the MCMC analysis involves running many different simulations in order to efficiently calculate the posterior over a wide parameter space. And so ultimately, we ran more than 7 million simulations using slightly different values of the model parameters drawn from the priors. This figure shows some of our results for the predicted content of light elements in the core. So the bottom axis is the initial core composition, ranging from 0 to 20 weight percent. And then the vertical axis is the normalized posterior probability density. From left to right, the different colored histograms represent magnesium, and then oxygen and silicon. In these 4 plots on the top right, we have in gray histograms the partition coefficients for the siderophile elements that our model predicts, and then the purple shaded regions are the likely ranges, the 1 sigma ranges for their actual values on Earth. So you can see that our models do a pretty good job of matching the observed siderophile element behavior. But clearly, the abundances of the siderophile elements alone do not tightly constrain the abundance of oxygen and silicon in the core. And furthermore, our simulations aren't designed to capture every single detail of Earth's accretion. But nevertheless, even with this simple model, we get a robust conclusion, which is that it's easy to partition 1 to 2 weight percent of magnesium into the core without violating any geochemical constraints. So using plausible initial compositions, we can then simulate the precipitation of magnesium-bearing material from the core. So I've shown 2 such simulations on the right side. On the bottom axis, we have core mantle boundary temperature, and the vertical axes are both percent of initial core mass precipitated from the cooling core, ranging from 0 weight percent up to 10. And we chose these 2 initial compositions so that the predicted core composition at the present day CMB temperature is roughly consistent with the models of Badger et al. That were tuned to seismological data. So the solid line on each plot is the sort of the results for the nominal value of the exchange coefficients from the literature. And the gray region bounded by these dashed lines is the 1 sigma confidence interval computed using bootstrap Monte Carlo resampling using the formal experimental errors. And because the experimental errors are large, our theoretical uncertainties are correspondingly large. So we don't model the mineralogy of the precipitate in detail, but in terms of oxides, the composition is roughly 80% MgO, 15% SiO2, and about 5% FeO. So magnesium, despite being the least abundant light element in the core, compared to oxygen and silicon, comprises the bulk of the precipitate because it is the least soluble. And it turns out that removing precipitate from the core, transporting it across the CMB and underplating the mantle releases more gravitational potential energy than growing the inner core, an order of magnitude more, which means that this precipitation is a great source of power for the dynamo. So in terms of equations, if we assume a homogeneous density profile for the core, we can write the energy release from precipitating magnesium-bearing material, which is this delta E sub m here. Here, G is the gravitational constant, m sub c is the mass of the core, delta m sub m is the mass precipitated, and delta rho sub m is the density contrast between the precipitated material and the core. R sub c is just the radius of the core, and rho sub c is the average density of a core. And for comparison, we have the energy released by growing the inner core, delta E sub ic. Here, delta m sub ic is the mass added to the inner core, and delta rho sub ic is the compositional density difference between the inner core and the outer core, which is about half of the 5% total density difference. And the crucial point here is that delta rho sub m is roughly 10 times delta rho sub ic, which means that if you precipitate just a 10-kilometer thick layer of silicates and oxides out of the core, you've given yourself as much energy to power the dynamo as if you've grown the inner core to its entire present-day size. Just a few more numbers. So using the updated values of thermal conductivity for the core, the heat flux out of the core is about 15 terawatts. So if you want to drive convection by thermal convection alone, you need to cool the core by more than 300 Kelvin per billion years, and more if you think there's significant ohmic dissipation required to drive the dynamo. Whereas if you use precipitation, this 10-kilometer layer is less than 1% of the mass of the core. And in the previous slides, I showed you that per 100 Kelvin of cooling, you get about 1% of the core mass precipitated, subject to uncertainties. So if you have this precipitation, you can keep the convection going for cooling rates as low as 50 Kelvin per billion year. So in this talk, I hope I've convinced you that adding just a little bit of magnesium to the core isn't a crazy idea. It's consistent with experiments and first principles calculations, although surely much more work needs to be done. And having magnesium in the core is a natural consequence of bringing in high temperature material in the aftermath of giant impacts. And if you do have this process, you can have the dynamo going for 3.5 billion years, even if radiogenic heating is minimal and core cooling is slow. And this process might have some implications for the evolution of Earth's deep interior. Specifically, models of the dynamo need to consider a source of compositional buoyancy at the top of the core, and also the possibility of transporting a significant amount of material across the core mantle boundary. With that, thank you, and I'm happy to take questions.
So we have 2 minutes for questions or comments. Bruce?
Could you speculate about the time dependence of your energy source from the beginning to sort of present day?
Sure. So it depends a lot on the temperature at which the material starts precipitating relative to how it is today. So probably precipitation functioned for a lot of Earth's history. The thing that's not clear is how this affects the age of the inner core. Because if you have precipitation along with inner core growth, then the inner core could potentially be very old, much older than 1 billion years. But precipitation should be ongoing today.